In this particular video, we're going to look at some of the concepts in Chapter 11, and what we're going to try to do is understand how exactly we would apply those concepts. So what we're really going to consider here is, if I'm going to perform an experiment and I have to choose a significance level for a significance test, what would I need to factor into that decision? And the first thing that we're going to have to consider is the definition of type 1 and type 2 error in the situation, also the power that we want our test to have, and then that will help us to kind of make up our minds about our alpha level. We're going to start by just considering what type 1 and type 2 error look like in a given situation. And so the first thing we have to start with, if we're going to talk about type 1 or type 2 error, is that we have to have hypotheses to frame the discussion. So we had discussed in class an example of paramedic response times in a given community, and that we had a target time for those response times on the average, what we want them to be. And then we wanted to take a sample of data to see if the response times had sort of changed or improved from an earlier experiment. And so here were the hypotheses we came up with. Our null hypothesis was going to be that the average response time for paramedics in a given community to get to a scene where an accident victim or some other person with a medical emergency was waiting was 6.5 minutes. I'm sorry, 6.7 minutes. And this is from an earlier study. And so what they wanted to figure out is, as the alternative, had that response time changed or dropped below 6.7 minutes in any significant way. It's a fair question to ask, because certainly if we don't have that, if we had not had that drop in response time, then it may be necessary for the city to take some sort of action to correct the situation. So the first thing we're going to do is we're actually going to create a type 1, type 2 error grid. And so the first thing we have to think about is, on the grid, is what's actually true in a given situation. So let's draw this little grid here. The top corner is going to represent what happens when the null is in fact true, but we reject it anyway, which obviously is an error. We really do not want to do that. This is our type 1 error. Looks like this. Here's type 1 error. Now, if we have the null being true in this first column, but we fail to reject the null, we would just say that's correct. We should fail to reject it when it's true. So in this particular case, we would just say correct. This would be a correct decision. There's nothing to worry about here. Now, the other possibility is that if the null is in fact false, meaning that the alternative hypothesis is true, again, we have to think about which one of these rejecting or fail to rejecting would be correct and which one would be a mistake. Well, if the alternative is true and we reject the null, that's correct. That's what we should, in fact, do. If instead, when the alternative is true, we fail to reject, this is what we're going to call a type 2 error. And in any given situation, one of those could be worse than the other. So first thing we're going to do with our paramedic example is we're going to say, what if, in fact, this null is true, that the mean response time has not changed, it's still roughly 6.7 minutes, but yet we reject it in favor of the alternative that mu is less than 6.7 minutes. What would that really entail, and what problems could it potentially cause? So let's take a moment to just talk about type 1 error in this case. So remember, in type 1, the response time is still approximately 6.7 minutes. But we assume it has decreased. That's what type 1 error would indicate in this particular case. And we want to think about what would the consequences of that be. The consequences could be that the city might assume all is well and takes no further action to improve on the paramedics' response times. In that particular case, since all is not well, we know there really is a problem, we could see an increase in preventable deaths, increase or a maintained rate, either one, of preventable deaths. So that's a pretty serious consequence. Because if we're saying that if they had just responded a little faster and provided care, that they may have survived, that's a serious problem. This is certainly something we want to avoid. But let's see if type 2 error is in some ways worse than type 1 error. It can be in this particular case. If we go to type 2 error, then what we would assume in that case, remember that's when we fail to reject when in fact we should. This is when the response time has really decreased, but we think it hasn't. So the question is, what are the consequences here? Well, the consequences are that the city might spend money on extra training, or extra equipment, perhaps, that they might get. So there's a couple of things that could happen here. You could have some frustration among employees who think they're doing a better job and they are, but that's not being acknowledged. And again, that can vary in its severity. But what we really don't see happening here is we don't see threats to life and limb in this particular case. And so if we have to choose between the two types of error that we want to reduce as much as possible, I think it's clear that we would like to err on the side of type 1 error. We want to reduce that as much as we can. So let's remind ourselves what the linkage is between the two types of error, and then we'll talk about the power of the test. Remember that alpha is equal to the probability of a type 1 error occurring. And so with that in mind, if we want to avoid a type 1 error, which we do in this case, we need to reduce alpha. So to avoid type 1 error, we need to reduce alpha. And so really what we're saying in doing this is we're saying if I reduce alpha, that means it makes it harder for me to reject the null hypothesis. I only do that when I have very strong evidence. And that's a reasonable thing for me to do. Okay? If instead, let's say I want to look at type 2 error. Oh, and by the way, if I reduce alpha, one of the things that I'm going to have as a consequence of that is my probability of type 2 error is actually going to increase slightly. I can't have both. There's no way that I can reduce one and reduce the other at the same time. I can only reduce one at a given moment. What we're going to do next is we're going to look at type 2 error through the lens of power and remind ourselves of how that's going to work. So if alpha is the probability of a type 1 error, there's another Greek letter that we're going to use called beta, which is going to be the probability of a type 2 error. There's good news about beta, which is that you are not going to ever have to calculate it. Beta actually varies depending on the specific alternative value that we chose. So with our paramedic example, we might calculate the number beta for the specific alternative time of 6.2 minutes as an average response time, or 6.1 minutes, or 6.0 minutes, and each one would have its own beta. Instead of worrying about what beta actually is, what we're going to do instead is we're going to talk about the power of the test, and power of a test is defined to be 1 minus the probability of a type 2 error. And there's some things about power that we want to know, the characteristics of it that we really need to be thinking about. First of all, we want power to be large. We want it to be between 0.8 and 1. And the reason for that is because it's actually the probability of something that we do want to happen. Remember, we do not want type 2 error to happen. So 1 minus that probability would be the probability of something we would like to have happen. Power itself is trying to measure how likely it is that we fail to reject the null when in fact that's what we should do. I'll say it again. Power is the probability that we fail to reject the null when in fact that's what we should do. And so needless to say, we want that to have a relatively high probability. And there are ways that we can increase the power of a test. And so let's just list what those are. These are related to an applet that you can still go through the activity for if you weren't in class. It's activity 11C. It's on page 729. It has you go to the book website and go through a series of calculations. And if you weren't here to do that day, you might give it a shot. If you were here and just want to review, this is a good way to help remind you of why these things work the way they do. So our desire is to increase power. And by the way, by doing that, because power is 1 minus beta, in order to increase power, we have to decrease type 2 error probability. So there's a couple ways we can do it. One of the ways that we can do it is we can increase alpha. Remember that we talked about to decrease the probability of a type 1 error, we had to decrease alpha. So now you can hopefully see why the two things work kind of at cross purposes with each other. And so what we're saying here is that we want to fail to reject perhaps more, maybe not more often, but certainly when we ought to do it. Remember, by increasing alpha, we make it slightly easier to reject the null. Okay? The next thing that we could do is we can increase the sample size. So increase n. And in general, we've already talked in class many times about the benefits of a large sample size. By increasing n, we're decreasing the variability that can occur. Our standard deviation will generally become smaller. And what that's going to give us generally is greater accuracy. And again, we're going to fail to reject at times when in fact we should do so. Another number that we can change is we can try to decrease sigma, which is a difficult thing to do relative to the other two, but certainly there are some ways to do it. One of the things we can do is either improve our measuring process to, again, to decrease the variability in that process using a better measuring tool, for example. Also, we could simply restrict our attention to some sort of a subpopulation for the purposes of the test, which would also decrease the variability. Now, the last thing we can do to increase the power is to make sure that we consider an alternative value, because remember that every beta that we have depends on the specific value of the alternative. So consider an alternative value that's relatively far from the hypothesis. And the reason why that's important in this particular case, it's like if we go back to our paramedic example, if I know that the original mean that I'm measuring is 6.7 minutes, well, if I'd say, well, let's find the beta value for 6.6 minutes. Well, the difference between those two is so small that natural variability is going to cause us at times to either make the wrong decision, either reject or fail to reject when we really should, because there's just not that much difference between the two values. So notice that when we're talking about power, one of the questions I might ask you is I might say, we need to increase the power of this test. What's one thing we could do? And so really these top three are going to be probably the most prominent answers that you're going to use. I could increase alpha, increase the sample size, or decrease the variability in sigma. Probably the top two are going to be the most likely to be used. And this last one, and just make sure that when I calculate my beta value that I'm not choosing a value that's so close to the hypothesized value, but technically in the alternative, that the difference between them is negligible. So when I'm choosing an alpha level, the very first thing I have to do is consider which type of error I'm trying to decrease the likelihood of, type 1 or type 2. And so a simple way to think about alpha in general is really kind of this. If I want to avoid type 1 error, I need to decrease alpha. Okay? And then to avoid type 2 error, a simple way to look at it in terms of alpha is that I need to increase alpha. And so that's something that I can certainly consider for the hypotheses that I have.